Okay, well then we are so thrilled today to have Maryam Khaqan from Emory University to talk to us about moonshine.
Awesome. Thank you so much. Okay, so I was told that this is a pre-seminar and it is aimed at graduate students. So I'm gonna try to tell two different stories in the pre-seminar and the main seminar. My goal for the pre-seminar is to tell you a story of just like the origin of moonshine. So this is titled What is Moonshine? And my plan is to just give you a very general, broad overview of what the field is. And hopefully by the end of this talk, you will get out of this talk with questions more than answers, more just where do I look now kind of questions. And if you do get there, then I will consider this a success. At any point, if you feel like I said something that didn't make sense, please feel free to stop me. I have a plan for this talk, but it's not a rigid, I need to get through all of these things plan. Um, the second talk is more rigid, but you're welcome to stop me at any point in either talk. Okay, so let's begin. The title of my talk is What is Moonshine? And I want to start by giving you a spoiler that actually a lot is still unknown about the conceptual origin of moonshine, which is my sort of careful way of saying that no one really knows. Okay, so if no one really knows, then what am I doing here? Well, my plan, like I said, is to tell you the story. So the story starts at the first instance of moonshine, which was moonshine for the monster group. Um, it's the original examples. I'm going to spend a bunch of time talking about that example. And then once I have, during the time that I'm talking about that example, I'm going to try to make a point that all of the characters in the story are special in some regards. So the monster group is special, the functions that show up are special in their own world. And I will try to convince you that it is reasonable to hear the story for the first time and think, oh, this is just, a big cosmic coincidence. A lot of these special things got together and just that happened to, Monsters Moonshine happened to exist. And then I will spend not a lot of time talking about Conde Moonshine, just to give you a second example of the phenomenon. Because I think that as soon as you have a second example of something, you can be like, oh, where are all of the other examples? How do I generalize this now, right? The first one you can kind of just think, oh, maybe this is a coincidence, but the second one might convince you that there are other examples out there. The third part of my talk is going to be giving you just a very brief overview of what other things are out there. And at the end, I am going to state a theorem that I recently worked on, which is, and I will talk about how it fits into the story of Moonshine. Okay, so let's begin with the story of the monster group. So historically, really the story of Moonshine begins at the complete classification of finite simple groups, which says that almost all finite simple groups fit neatly into three infinite families: the cyclic groups, the alternating groups, or finite groups of Lie type. And there are 26 groups that don't. There are 26 groups that don't fit into these families, and here's a picture that I stole from Wikipedia of these groups. The lines denote subquotient structure. So Conway 1 is a subquotient of the monster group. Okay, so the largest one of these is called the monster group. And it is called that because it is very large. It has about 8 times 10 to the 53 elements. The number of elements is large, which is weird because these are finite groups and the sporadic simple groups stop after the monster group. This is the largest one. So it's a weirdly large number for it to be, I think. Okay, when you have something that is a weirdly large object, one way of studying that object is looking at its representation theory. And here's a character table for the for the monster group. The way that character tables work is that the columns are all conjugacy classes of the group, and the rows are irreducible characters of the group. So this entry, for example, is the dimension. I don't know if people can read that. Let's see. Let's use a different color. Is the dimension of of V1, the trivial representation of the monster group. Okay, so that's one character in my story. The monster group is one of the characters. The other character is the J function. And in order to tell you anything about the J function, I have to define what a modular function is. So remember that the group SL2Z, which is the group of matrices, 2 by 2 matrices, such that AD minus BC is 1 of determinant 1. It acts on the upper half plane, which is the stuff in the complex plane with imaginary part greater than 0. And you should check, if you get bored in this talk, you can check that if you start with something in the upper half plane and you have this action, it lands back in the upper half plane. Okay, so a modular function of level 1 is a function that is invariant under this action. If you move tau to tau a tau plus b over c tau plus d, f of tau remains the same. And the J function is the simplest non-constant modular form in some sense, in the sense that every other modular function can be written as a rational function of J of tau. The other thing I want you to notice here is that 1, 1, 0, 1, this matrix belongs to SL2Z because 1 times 1 minus 0 times 1. And if I apply this to tau, I get tau goes to 1 tau plus 0 over 0 tau plus 1. So tau goes to tau plus 1. So if J function is a modular function, then J of tau is J of tau plus 1. So it's periodic in tau. So I can in fact write Q as e to the 2 pi I tau and have a Fourier expansion of J of tau. So this is the Fourier series of J of tau. And now what I'm going to do is I'm going to write the, I'm going to, on the same slide, write the Fourier series and write the character table of the monster group. Now you might have heard the story before, but if you haven't ever heard the story, then I'm going to pause here for just a couple seconds for you to look at the slide, ponder over it, and notice things. If you notice anything, that would be cool. Okay, if you're John Mackay in the 1970s, you would notice that this number, 196884, is very close to this number, 196883. In fact, it is the sum of these first two entries. It is 1 plus 19683. I don't know if my highlighting will show up really, but so I'm talking about, I'm focusing on the first column. Okay. If you tell this to John Thompson again in the 1970s, he will say, well, actually more of this is true. If instead of looking at just the first two entries, I add the first three entries together, so these three entries, then I get this number. Okay, I'm bad at arithmetic and mentally, so I'm gonna do this at mod 100. I'm just gonna show you this mod 100. So if I do 6 plus 3 plus 1, I should get a 0, and I should carry a 1, so I should get 15 plus 1. That would get me 60, and you can do the rest of the calculation yourself. Okay, so maybe this works always. Maybe I can keep going. What if I add the first four numbers? What happens then? Well, again, I am bad at mental arithmetic, so I'm only going to do this mod 100. But already you see that that doesn't work. You don't get this entry. You would want, you know, we like patterns, so you would want this entry. But if I try to do 1 plus 3 plus 6 plus 6, that's 12 plus 3, 15 plus 1, that's a 6. And this has a 0 mod 10. Okay, that doesn't work. So if you're me, you might abandon this. You might be like, oh, well, I guess not, nothing is happening. But again, if you're John Thompson, you would say, well, instead if I look at 2 times the first entry, 2 times the second entry, plus 1 times the third entry and 1 times the fourth entry, then that gives me this number. If I add 6 plus 6 plus 2 times 3 plus 2 times 1, I get 0. Okay, that I'm convinced by. So now I can think of this whole thing as a formula. So I can say, well, this entry was 1 plus 2, this entry was 1 plus 2 plus 3, this entry was 2 times 1 plus 2 times 2, plus 3 plus 4. So can I use this just pattern and try to do this for other columns of the character table? So I'm going to now jump to column 2b, and I'm going to do the same thing. So I'm going to call this function t2b of tau, and I'm just copying down what's in j of tau, but using the 2b column. So q to the minus 1 plus some coefficient of q. The sum coefficient is 1 plus 275. So I get 276. And then I have the first 3 entries, which is 1 plus 275 minus 324, which is 2024, I think. Is it 2024? Maybe. We'll see in the next slide. And if I add 2 times the first entry plus 2 times the second entry plus 1 times the third entry and 1 times the fourth entry, so these things. Again, if you're better than me at mental math, you might figure out that that is 11202 q cubed. Did I write the incorrect number? 2048, not 24. Okay, anyway, those numbers work out. These are the numbers that show up if you do this. Okay, so now you can ask, well, is T2b anything relevant? I just wrote down some numbers next to some coefficients of Q. And actually, it is also a well-known modular form. If you know anything about modular forms, this delta of tau is really the first one you learn about in some sense. So delta of tau or delta of 2 tau plus 24 gives you this function. Okay, so this is enough evidence for John Thomson to conjecture that there exists an infinite dimensional monster module, V natural, whose graded dimension is j of tau, and each of whose Mackay-Thomson series is a normalized Hopf module for a genus 0 subgroup of SL2R. Okay, this is a mouthful, and it was proven like a long time later in 1992 using work of a lot of people. But the thing that I want to focus on is this thing, is the normalized Hopf module for a genus 0 subgroup for SL2R. So I want to say first that being a normalized Hopf module for a genus 0 subgroup in SL2R is a very special thing in the world of modular forms. The probability that I pick a random modular form and it turns out to be one of these is very low. And what this conjecture is saying, it's saying that for all of the columns of the character table of the monster group, so all 194 of those columns, all of them turn out to be this weird thing, this normalized Hopf module for a genus 0 subgroup. Okay, so I have to give you a definition of what this means. So gamma in SL2R is called a genus 0 subgroup if and only if there exists an isomorphism between these spaces. So remember that gamma acts on the upper half plane, and you can look at this orbit under this action as a surface, and you can ask, when is there an isomorphism to C union a point at infinity, which is really the Riemann sphere. So the Riemann sphere is a genus 0 surface, and so you call gamma a genus 0 group if this isomorphism exists, and you call the isomorphism a Hopf module, which is a German word. And I spell it on these slides incorrectly, I think. At least people in Germany might think that it's spelled incorrectly. I apologize. If gamma satisfies some like technical condition, I can define what one at infinity is, but don't worry about it. If gamma satisfies some adjective, then you can normalize your Hopf module, by which I mean that you can take T gamma of Q to be Q to the -1 plus order of Q as imaginary of tau goes to infinity, and you can ask that it has no other poles on H hat. And for gamma equaling SL2Z, T gamma is J of tau. And so T gammas are the normalized Hopf modules of a genus 0 surface. And this property that they're normalized Hopf modules can be translated to the following. So basically, each of the Mackay-Thomson series, each of the graded traces of the monster group, is uniquely determined amongst modular functions of the same level by its behavior at the cusps. This is what we call the genus 0 property of Moonshine. And this really is why I I kind of said that no one really knows what's going on because there's no like real conceptual understanding that we have of why genus zero groups appear. Why are these things genus zero at all? And again, like I said, being genus zero is rare and useful. It gives you a kind of determinability that you don't get just for a random modular form. Okay, so at this point, after listening to the story, you might wonder if this is all a coincidence. And even if you don't wonder that, I want to spend another like minute convincing you that this is a rational train of thought, because notice that the monster group is special in the world of finite groups. It's the largest of the thing that doesn't do a normal thing, right? And I have just spent some time at least saying that the functions that appear are normalized hot modules of genus zero subgroups, so they are special in the world of modular forms. And I've spent no time telling you anything about the vertex operator algebra that appears, the module itself, but it's because I don't have a lot of time. You should trust me that it is also conjecturally special in the world of VOAs. So you might wonder that maybe all of these special objects just happened to, in a coincidence of the cosmos, come together and give you a coincidence. And so at this point, like I promised, I'm going to get into a second example of moonshine. And I hope that when you see that example, you'll be like, yeah, that looks exactly like the monster moonshine story. And so maybe there's more to this story than just one example. So my second example is Conway moonshine. And to explain it to you, I have to jump very far ahead in time. So remember, monstrous moonshine was proven in 1992 by Borchers. This paper came in 2014. This was by John Duncan and Sander McCrane, and they proved that there exists an infinite dimensional Conway zero module, V supernatural, whose graded dimension is T2b of tau over 2. T2b, remember, was the I went through the second column in the character table, one other column. That's the function that appeared. And for if I define the super traces now instead of the traces, then the Mackay-Thompson series turns out to also be a normalized hot module for a genus zero subgroup. So the functions are still special in the same sense that the functions of the monstrous moonshine was special. Conway zero is not a sporadic simple group, but Conway zero modded out by its center is Conway 1, which is a sporadic simple group. So arguably the group that appears is also special in the same way that the monster group is. And this time there's a term that says that V supernatural is special. I'm not gonna go into details of that, but really at this point you should really be convinced, hopefully, that the Conway moonshine it feels like it is another instance of moonshine. And so if you are convinced of that, then you should ask, well, if there are two examples, why not infinitely many? Also, you should ask, well, if there are two examples and there are more examples, can we find them all? Can we characterize them all? Where do we look? All of those are like good questions to ask at this point. And I'm going to, as promised, tell you about more examples of moonshine. So in order to do that, I have to go back in time a little bit. So remember that I was in 1992, and then I jumped ahead to 2014. Now I'm going back to 2011. So it seems like I made a pretty big jump, but actually historically, like it wasn't as big a jump as you think. In 2011, Iguchi, Oguri, and Tachikama observed that the elliptic genus of a K3 surface, which do not ask me what that is, a K3 surface is a thing, but also elliptic genus is a thing that physicists care about. So these people were looking at this because physics. So that's gonna be my explanation for that is. For me, this is a Jacobi form of weight something and level something. But anyway, this is a function that people cared about. And these mathematicians observed that it looks like it is related to the largest Matthew group, M24, which is also a sporadic simple group, in a way that feels a lot like this should also count as moonshine. And what do I mean by that? I mean that if I isolate this part, the part in red, q to the negative 1/8 times -2 plus some coefficients of q to the n, and I write them out And I am going to do the same thing where I put the character table of the Matthew group now on top of here. I'm going to, I think I have about 9 minutes. So I have time to stop here and let you look at this for a minute. So stare at the Matthew group and h of tau and hint, stare at the first column again and see if you can notice something. And, feel free to unmute yourself and talk to me or put things in the chat.
So, this isn't about the first column, but do the dots in the table mean zeros?
The dots in the table mean zeros. The A's are some quadratic, A's are some complex numbers, and this is from GAP, so it has weird notation.
Okay, cool, thanks.
Yeah.
Like sometimes like two numbers appear right after each other, and then like those two sum up to like the coefficients. Like you can see 45 to 90, 231 to 462.
Okay, I am very pleased that you made this observation. So 45 sums up to 90. 231 sums up to 462. Very good. I don't know, my highlighting might not appear on my screen. I feel like we'll just live with that. 1540 divided by 2 is like 770. So 770 appears in here as well. I'm gonna keep going. What is 4554 divided by 2? That is 2277. That's this one. Okay, it doesn't appear twice, but it's, it doubles to a coefficient. And then 11592. Oh my God, how do I divide this by 2? That's 5, 7, 9, I think. Can I cheat? 5796. That's this number. Okay, is this moonshine? I don't know. At this point, you should ask that. Is this moonshine? Well, Terry Gannon proved in 2012, based on work by a lot of people, that there exists an infinite dimensional graded M24 module. This sentence should kind of be familiar by now, right? I've said this a couple times. There exists an infinite dimensional graded module such that for any G, the Mackay-Townsend series is a Mach modular form for some subgroup of SL2R. In particular, the h of tau that I showed you before is actually the dimension. Okay. So I've kind of written all three of these theorems down in kind of the same language, so as to make them look the same, right? This is kind of by design. But I do want to give a few caveats here. So the first one is that this last theorem, which I'm going to call the Matthew Moonshine version, is actually, the proof of this theorem isn't constructive. So up until now, I've told you about V natural, which had the action of a monster group on it. This was constructed by Frenkel, Pasky, and Merriman as a vertex operator algebra. This has an underlying structure. You have an explicit construction. The Conway zero thing was constructed by, it's a super vertex operator algebra, and it was constructed by John and Sander McCrane in the same paper that the Conway Moonshine theorem came from. But in this case, in the Matthew Moonshine case, we have a theorem that says there exists one of these, but we don't have an explicit construction for this. The other thing that we don't have is that these are Mach modular forms, and the gamma G's that appear are not all genus zero. And even if they were, there isn't a natural sense in which we can think of a Mach modular form as a hot module for a genus zero subgroup. So if like your entire faith in Moonshine is like dependent on the genus zero property, this should shake your belief a little. You should wonder at this point whether you really should call this Moonshine or not, right? The other last comment that I want to make here is that, again, I'm jumping around in time, so I'm not chronologically crediting everyone with everything. So similar results, similar to this, results existed at this time for the 23 Umbro groups. So you can make a choice at this point. You can say, well, none of these results, the Umbro groups or the Matthew Moonshine theorem, are actually Moonshine. We shouldn't call them Moonshine. We should only look at like weight zero, genus zero stuff, and we should only call that Moonshine. Or you can be like, I'm going to be more welcoming, and I'm going to try to find a general framework that encapsulates the monster case, the Conway case, the Matthew case, the Umbro cases, and maybe other cases that will appear. And here's the big, I feel like this is a really cool theorem that John Duncan and Miranda Chang proved, that each of the Mackay-Thompson series of Matthew Moonshine, the Hg of tau that appear in Gannon's proof, is uniquely determined amongst Mach modular forms of the same weighted level by its behavior at the cusps. And I claim that this is an analog to the genus zero property of the monstrous Moonshine case. The fact that this works, again, is kind of mind-blowing. And this looks very similar to, I'm gonna jump back in slides. So the genus zero property said that each of the Mackay-Thompson series of the monstrous Moonshine is uniquely determined amongst modular functions by its behavior at the cusp. And now I'm saying that these Matthew Moonshine Mach modular forms are uniquely determined by their behavior at the cusps. So I claim that that's the, in some sense, correct analog of the genus zero property. Okay, so I've told you about a few examples. This is my slide of things to Google. So I'm just gonna give you some names if you're curious about other things that are Moonshine. Look up Matthew Moonshine, Umbro Moonshine, Thompson Moonshine, Onan Moonshine, and other things that I haven't put on this slide. All right, so let's ground ourselves back into what I was trying to do. So I've told you the monstrous Moonshine story. I've given you some other examples, and now I'm going to give you a theorem that I have recently worked on. So let TH denote Thompson's group, which is again a sporadic simple group. It appears here in the picture. Also notice, I just want to, since I made this picture again, I want to point out this is the Conway group. Well, Conway group is related to this group, and this is M24. These are the ones that we have talked about. And if you're looking at this picture and you're like, well, what about all of the other ones? That is also a good question. And I don't know, we should wonder what about all of the other ones. Okay, so if I take TH to be the Thompson group and let F of tau denote the unique weakly holomorphic modular form of weight 3/2 that transforms nicely under gamma naught 4 and lies in the Conan plus space, whose Fourier coefficients begin like this, then there exists an infinite dimensional Thompson module whose graded dimension is 6 times F of tau, and each of whose Mackay-Thompson series is a distinguished function on the upper half plane, which is vague, but I will tell you what I mean by that. I just didn't want to put it on the slide. I do want to point out that this is on the archive at sort of this address, but also, you can look at it, look at my website and find it. So the distinguished function on the upper half plane, by that I mean that each of these is a weakly holomorphic modular form that has weight 3/2 and transforms nicely under gamma naught 4G. This should say, this parentheses should end there. That transforms nicely under gamma naught 4G with a character that is determined by G. And it is uniquely determined up to a cusp form by its behavior at the cusps. So it satisfies what I claim is the analog of the genus zero property. And I guess in my last minute, I'm just gonna say what my plan for the next talk is, because I've tried to convince you that, all of this is Moonshine, and all of the examples that I've given should fit into a general framework. But if you are skeptical of that, if you're like, no, only the monster story is Moonshine, maybe the Conway story is Moonshine, then I claim that it is still worthwhile to do these things, because in the next talk, I'm going to show you how you can use this theorem to actually say things about elliptic curves. That's where I'm gonna stop. All right, thank you for listening to me. Are there any questions, comments, anything?
Okay, let me try to see if you can hear me.
We can hear you.
Okay, so thank you for this wonderful introduction. Questions, anyone?
Yeah, so from my understanding, we were kind of relating, there were like three things. You drew arrows, right? Like you had like kind of these sporadic groups, which kind of belong to group theory. And then you had these modular forms, which I think are like number theoretic objects. Yeah. Is that correct? Or like arithmetic objects, and then this like VOA, like vertex operator algebras, and like kind of what kind of field does that kind of connect? Like I'm just trying to get a
Ah,
general picture as to
yeah.
like what areas are we connecting with this kind of.
Yeah, very good.
theory?
I think so algebra, which is a weird thing to say, but like representation theory. And so VOAs, I'm not gonna try to define VOAs because the definition is hard, and also I have no idea where in the slides it was, so I'm not gonna try to flip back to it either. So that's a very good question. This is group theory. And these are modular forms. And so almost like, I don't know if I'm like, okay, I'm gonna make sure that I'm not lying to you, but physics. The VOAs appeared first because physicists were working on them already. And what Borchardt's proof does is he is trying to find structure, and I think originally, like even the VOA he builds comes out of a Lie algebra. So he wants an action of the monster group on something, on some representation, and he built a Lie algebra, and then I don't know if he was talking to physicists, if, like where Borchardt's got the vertex operator. Oh, sorry, no, Frankel-Hosky and Merman wrote this, not Borchardt's. Borchardt's used some physics, but yeah, Frankel-Hosky and Merman wrote found a construction for this vertex operator algebra that has an action of the monster group on it. So yeah, I would say representation theory and physics and Lie algebras. That's a probably bad answer.